All right, so from the last lecture, we have this statement here. This was the first of our transformation equations. And again, it's just giving us the stress on that inclined plane, the normal stress, as a function of sigma x, sigma y, tau xy, and theta. Now, if you have studied stress analysis or you've looked at it in a textbook, you'll likely have seen this transformation equation in a slightly different form. And we can obtain that slightly different form by rearranging the right-hand side of this equation using some trigonometric identities. So it's fairly trivial stuff. So I won't go through step by step how you do it, but I'll list the identities that you use. So the cosine squared of theta is going to be replaced by a half times 1 plus the cosine of 2 theta. Sine squared of theta is going to be replaced by a half times 1 minus the cosine of 2 theta. And then sine theta cosine theta is equal to a half times the sine of 2 theta. Okay, so when you use those trigonometric identities, you replace the terms, the corresponding terms on the right-hand side of this equation, and you get the following form of the transformation equation, which is absolutely equivalent to what we have above, but it's just a slightly more widely used version of it, right? So it's going to be this. It's going to be sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times the cosine of 2 theta plus tau xy times the sine of 2 theta. Right, we're going to box that guy up and we're going to call that transformation equation 1. So that's our sort of first transformation equation proper, if you like, or TE1, okay, because we're going to be referring to this equation. And similarly, we can take the second transformation equation, which we have from the previous lecture, which was this guy, right? That guy becomes, by a very similar process of rearranging, we get this guy. All right then, so what has that given us? That has given us, if we imagine some set of faces at some angle theta, some inclined set of faces, right? Well, we've just worked out what is sigma x1, and we've worked out what is tau x1, y1. Now we can go another step further and we can work out what would the stress be on the y1 face, right? Let's call that sigma y1. And the easiest or probably most straightforward way of doing that is to obtain sigma y1, we're going to sub theta plus 90. So the angle for that face is actually theta, whatever theta was. Remember, theta was that angle there. So theta, add 90 to it, that gets you to this face here. So sub that angle in for theta in the first transformation equation, TE1. So up here, instead of using theta, sub in theta plus 90 degrees. Right, and when you end up doing that, let me see, what have I got to do here? I have to work out what does the cosine of 2 theta become, and what does the sine of 2 theta become if I take out theta and I put in theta plus 90. So we'll say, let's just focus here on what does the cosine of 2 theta, what does that become if I take out theta and put in theta plus 90, right? Well, what would I end up with? I'd end up with cosine rather, of, now instead of theta, it's going to be theta plus 90. That's okay. Cosine, and multiply through by the 2, you're going to get the cosine of 2 theta plus 180. Okay. And if we use another trigonometric identity, this is the identity. The cosine of A plus B is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. All right. Now, if A was equal to 2 theta and B was equal to 180, what would you end up with? You'd end up with the cosine. Once we have these equations worked out, we're going to go ahead and actually plot them. Right, so what do we end up with? We'd end up with the cosine of A, which is 2 theta, times the cosine of 180. That's going to end up going to minus 1, minus the sine of 2 theta times the sine of 180, and that sine of 180, that ends up going to 0, so that means all of that goes to 0. And so what we can say is that the cosine of 2 theta that we started off with, which was this guy here, when we sub in theta plus 90, we end up with minus the cosine of 2 theta. All right, then that's okay. And then similarly, by a very similar process, the sine of 2 theta becomes or goes to minus the sine of 2 theta when theta goes to theta plus 90. All right then, so what does all that mean? All that simply means is that we can replace in our transformation equation 1, we can replace the cosine of 2 theta with minus the cosine of 2 theta, and we can replace the sine of 2 theta with minus the sine of 2 theta. All right, so third transformation equation, sigma y1, so the normal stress on the plane that is perpendicular to the x1 plane. Okay, so again, that's going to be this plane here. The normal stress on that plane is equal to the following. That is transformation equation 3. So let me just call this transformation equation TE3. Right, 3 transformation equations. Let's just take a pause here. So we have all of the equations we need to work out the stress on any set of inclined planes. But there's more we can tease out of this. There's more understanding we can tease out of this. And as I keep saying, ultimately, we're shooting towards Mohr's circle here. That's the final destination for this discussion. Because once you see Mohr's circle, you know, you'll get a bit of a light bulb moment and you'll see, okay, that Mohr's circle is really, really helpful. So let's make a couple of observations based on these equations. The first observation I'm going to make is the following, right? The sum of the normal stresses is constant, right? And therefore it's independent of the angle theta. What does that mean? What does that mean? Well, let me state it first. And therefore it's independent of the angle theta. Okay, well, what you could do to confirm that is you could consider adding together transformation equation 1. Remember, that was a transformation equation for sigma x1. Adding that to transformation equation 3, and remember that was one we just looked at, which gave us sigma y1. You add those two equations together, what would you end up with? You'd end up with sigma x1 plus sigma y1, and you'd see that on the right hand side, when you added the right hand sides of TE1 and TE3, you just end up with sigma x plus sigma y. All right, that's essentially our mathematical expression for this expression here in words, right? So the sum of the stresses is constant, right? That's what we're saying here. So I take the two stresses on any two mutually perpendicular planes, the two normal stresses on any two mutually perpendicular planes, they're going to give you a number, a constant, and that's going to be the same number as if you rotated those set of planes by any angle and added the two stresses on the new two mutually perpendicular planes. They're constant, and that's quite a nice little feature. So what's the next key point I want to make? And this really is a fundamental point, and it's really fundamental to the whole discussion here. I keep talking about the stresses on a set of different planes, and I'm talking about rotating and orientating these planes at different angles. Really, what you have to get clear in your head is the underlying state of stress at the particular point that we're looking at is the same. It's not changing. All we're doing is rotating the set of axes against which we're, we're observing the state of stress at that point. And it's the simple analogy I like to use to describe this is it's a vector. You can imagine the state of stress at a point in our structure as a vector. And I can consider that vector as the sum of two orthogonal components. And those two orthogonal components are going to have different magnitudes depending on what set of axes I align them with, right? So let's just get a couple of notes down on here, and I'll sort of sketch out what I'm talking about here. The underlying state of stress at a point is constant. And that's what we're kind of hinting at here with this statement. When we're rotating our axes, when we're rotating our planes, all we're doing is considering a different orthogonal set of components, or a different set of orthogonal components of a constant magnitude stress. A vector presents a reasonable analogy for this, right? So what I'm trying to explain here is the fact that let's imagine I have some point in space, right? And let's say that the magnitude of the stress at that point in space is represented by some vector, right? Now, I'm going to just call this vector sigma, okay? Now, I could consider that vector sigma as two orthogonal components parallel to the x and y axis here, right? So I'd have a sigma x component here, and I'd have a sigma y component here. Now, I can take that very same vector, right? I can take that very same vector, right, sigma. If I rotate my set of axes, which is analogous to rotating my planes, okay, the planes on which I'm determining the stresses. So let's imagine I rotate my set of axes. So let's imagine I've got some arbitrary set of axes here like this, right? So the vector sigma hasn't changed, but if I was to consider the orthogonal components of it now, well, okay, well, the sigma x component just got a lot bigger. Okay, there's your sigma x, and your sigma y component got a lot smaller. Sigma y got a lot smaller. But fundamentally, those are two components of the same state of stress, the same stress vector. That's all we're doing here when we're rotating our planes. The underlying stress in the system hasn't changed. It's constant. It's the stress at that point. But when we're rotating our planes, we're considering different components of that stress vector. And you can think about it as the different orthogonal components of a vector. It's just that you're rotating your set of axes, okay? When I'm rotating my set of axes here, here, and here, that's analogous to me saying, okay, well, I've got an element here with a set of axes like this, and then I'm going to rotate my element like this, and that's going to give me a rotated set of axes, okay? Well, I'm determining the set of stresses of the same underlying stress state just against a different or along a different axis system. So that's the analogy I like to use to kind of explain conceptually at least what it is we're trying to do here when we're rotating these planes. Right, so I think we've done enough. We've done enough derivation of equations. We've got the key equations we need. The next thing we're going to do now is take these equations and actually plot them. It's only when you actually go and plot them that you're going to get a sense of what it is they're trying to tell you. So let's do that then. So I'm going to imagine a scenario here, right? Let's imagine a scenario where I have some element, all right then, and I'm going to just give it some arbitrary values of stress. It's going to have a stress sigma x here and here. It's going to have a stress sigma y and a shear stress. We'll give it a positive shear stress. So again, that's a positive face. It's acting in a positive direction. That would be a positive shear stress, which means all of these guys are also positive shear stresses, right? So we'll call that tau xy. Now, just for the sake of demonstration here, I'll just say sigma x here, just let that equal to 1 Newton per millimeter squared. I'll let sigma y, let that equal to 0.25. Again, numbers out of the air, not really important for now. It's more the pattern of behavior we're going to be interested in when we plot these. And we'll say that shear stress is 0.75. Okay, so our task now is to use these equations, the three transformation equations, to plot, to see how the stresses vary as I change theta. So as I change the orientation of this element, how does the stress vary? So in order to do this, we're going to jump over to a Jupyter Notebook. Okay, so here we are over in our Jupyter Notebook. So if you've taken any degree tutors courses with me where we talk about, where we use Jupyter Notebooks, this will be quite familiar to you. So we're importing the math library for some math functionality. We're importing the NumPy library. Again, more functionality, helps us deal with arrays, as the note says there, and then some plotting functionality. Right, so I've got a little markdown heading, another markdown heading here, and now we've got our first code cell. Right, I'm going to assume that you're reasonably comfortable with Jupyter Notebooks. So, where to? We want to start plotting these equations. Right, so the first thing I want to do is define what are the values of stress on my planes. So what have I got? I've got sigma x. We said that was going to equal 1. We said sigma y was going to equal 0.25 and tau was going to be 0.75. Okay, we'll just add a quick note just to put in the units. Now I'm going to want to plot these transformation equations for a range of different angles. So I want to define a range of angles. So I'm going to say theta, and I'm going to use the NumPy library. I'm going to say theta is np.arange. The arange function is going to give me a number of equally spaced points between negative 180 and plus 180, but I need to go to 1 above the upper limit, which is 181 in my case. So that gives me my full range of angles. Now I'm going to be passing those into cosine and sine, and so I'm going to want those in radians. So I'll say theta underscore rad for radians, and I'm just going to take theta and I'm going to multiply it by pi over 180. So let me take from the math library, I'm going to take pi, which is a constant I can access within that library. I'm going to divide it by 180, and I'm going to multiply all of that by theta. Now that's going to give me a range of angles. Let's just plot those, not plot them, but let's print them. Okay, there's all of my different angles that I'm going to use to plot my transformation equation. Right, let's actually construct the transformation equation. We have, let's call it sigma underscore x1. This is going to be the normal stress on the inclined plane, x1 plane. Let's say 0.5 times sigma x plus sigma y plus 0.5 times sigma x minus sigma y. Now that's got to get multiplied by the cosine of 2 theta. Right, now I'm going to be taking the cosine function from the NumPy library because I need to pass it in a whole range of values rather than just one. So I'm going to say np.cosine 2 times theta, and remember we want the radians version, plus tau xy times the sine of 2 theta. All right, now all that is us building up the equation, the first transformation equation. We can do the same thing to get the transformation equation for sigma y. I'm going to just edit a copy of this. This is fraught with danger, copying and pasting, but I'll risk it. So this is going to be 0.5 times sigma x plus sigma y minus 0.5 times sigma x minus sigma y times the cosine of 2 theta minus, that should be a minus, tau xy times the sine of 2 theta. Right, that's my second transformation equation. And now let's get the third one. So we'll say this is tau x1 y1. Right, so this guy is equal to minus 0.5 times sigma x minus sigma y times np dot sine of 2. Oh, now I spotted an issue. That should be theta in radians, and this should be theta in radians. So again, 2 times the sine of theta in radians plus tau xy times np dot cosine of 2 times theta in radians. Now it's going to be a miracle if I didn't make a mistake somewhere in there, but it'll soon become apparent. So let's just go ahead and plot these straight away, right? So I'm just going to give myself a heading here, set up the figure and axes. Right, first thing I'm doing is defining a figure, and that's going to be equal to plt dot figure, if I can spell. All right, the next thing I'm going to do is add a set of axes. So axes is equal to fig dot add underscore axes. Okay, now what am I doing? I'm adding a set of axes. I'm setting the position of the lower left corner, and I'm setting the width and the height of my axes. Now I want them to be, let's just say 2 units wide by 1 unit high. It's really the aspect ratio I'm controlling here. And now I'm going to do some plotting. So let's just plot the transformation equations. Right then, so let's say axes.plot. Right, what am I plotting? I'm plotting my angles in degrees this time because I find those easier to intuit than angles in radians. I'm plotting, so the angle versus sig underscore x. So this is going to be my first transformation equation. Right, let's just see what that gives us. Okay, that looks about right. Let's start tidying this thing up. I want to just define the color. Royal, and I like this color, royal blue. So that might be royal blue actually. Is that royal blue? No, that's royal blue. So I'm just defining the color of the plot. What will I do next? I will set a label. So the label for this plot is going to be normal stress. And I think I can get a little bit of LaTeX in here. So I'm going to say sigma underscore x. That should give me a sigma x. Okay, so that should be enough for that. Let me do the same thing now. I'm plotting the sigma y1. Let's plot this in sea green. This is going to be sigma. Now let me see, that should be sigma y. That should probably be sigma x1. And this label should probably be sigma y1. All right, and then let's plot the shear stress. So let's plot theta versus tau x1 y1, and we're going to plot this in light coral. I was playing around with these colors, so light coral seemed to be one I liked, and we can call this Let's call this the shear stress. Again, that's going to be, now for some reason I can't get tau in here. I'm not sure why. So I'm going to leave the t on the outside and then have an underscore x1, y1. Let's see what that gives us. Okay, that is looking about right. We're going to interpret all this now shortly. It just looks like a whole range of sine waves right now, but bear with me. Right, let's just do some housekeeping first of all. So we're going to set an x label. This is going to be the same for pretty much every plot we do. Axes dot set x label, and then our x label is going to be angle of face, and we'll just say that that's in degrees. Let's set a y label. This is going to be stress. Let's give us a title. Axes dot set underscore title. And what's this going to be? Stress variation with angle. Now let's set some axis limits. So axes dot set underscore x lim. All right, we're going to pass that negative 180 and a plus 180. Now I'm going to want to set the, well, let's see what that gives us. Okay, that's fine. Let me, oh yeah, we want our legend. Axes dot legend. That's going to be, right, what are we going to do? We're going to set the location equal to, I want the location to be the lower left. I want a grid, so I'm going to say plt dot grid, and I want to get rid of this little output statement here, and to do that I'm going to say plt dot show. Let me see, what does that give us? Okay, we're getting somewhere. Now what have I left to do? Let's set our ticks, so I'm going to say axes dot set x ticks. Now I'm going to pass in a numpy list. So np.arange, I'm passing into this numpy function. This is just going to generate a sequence of numbers that go from minus 180 to plus 180 in steps of 20. That should give me, yep, that gives me my ticks along the bottom here. So basically that is our equations plotted, right? So let's interpret this now. We're going to interpret this by, first of all, plotting a vertical line for theta equal to 0 and seeing what are the values of stress. I mean, you can see it here, right? I'm just going to plot a line just to make it a bit easier to see. Let's just say plot some guidelines. Okay, so let's start off with a vertical line at theta equal to 0 degrees. So I'm going to say axes dot plot. Now what do I want? A vertical line. So that is going to have x coordinates at 0, 0. So that's 0 degrees. And it's going to have y coordinates. Now I just want an easy vertical line here. So I can just sort of by eye here set the vertical limits of this line to be minus, let me see what would work, minus 1.5 and 1.5 plus 1.5. Right, now what else do I want? I want to say the line is going to be orange, and I want to say the line style is going to be a dashed line. Let me see, will that work? Okay, very good. So let's zoom in here and see, right? So these three equations are the visual representation of our transformation equations. And we can see when theta is equal to 0 degrees, so that was the starting point, if you like. We said that sigma x was going to be 1, and sure enough, when we trace our blue line, we see at theta equal to 0 degrees, our transformation equation is giving us the value of stress equal to 1 Newton per millimeter squared. So sigma x1 in this case is 1 Newton per millimeter squared. We said that sigma y was going to be 0.25, so that's the green line. Let's go down and we can see, sure enough, sigma y at theta equal to 0 degrees is 0.25, halfway between 0 here and 0.5 up here. And our shear stress, tau xy, is going to be 0.75. Here we are here. So again, yeah, that's 0.75. So we can see now that we have these equations and we've plotted them, no matter where we move along the horizontal axis, no matter what orientation or what rotation our element has, we'll be able to determine the values of sigma x, sigma y, and tau xy for our element. So let's just do one more line here, one more guideline. Let's plot a line at theta equal to 90 degrees, right? See what happens to the stresses. Now this is, imagine what's happening here. We're taking our x, y axes and we're rotating those set of axes counterclockwise by 90 degrees. So that means that the new position of the x1 axis is going to be where the y1 axis used to be. And the new position of the y1 axis is going to be where the negative x1 axis used to be. And so in fact we can sketch that out. If I jump over to the notepad for a second. So here we are. So this was theta equal to 0 degrees. That was our starting point. And in that we had an x1 axis and we had a y1 axis. So at theta equal to 0 degrees, we've just seen on our plots what that sure enough, our transformation equations confirmed these values for us. So now what we're imagining when we plot, or when we extract from that plot the values at theta equal to 90 degrees, what's that actually mean? Well, the shape doesn't look like, the elements doesn't look like it's changed, right? Because it's just rotated by 90 degrees. That was a square to start off with. But our set of axes has rotated. So now this is the x1 axis and this is the y1 axis. Okay, so our set of axes have rotated as well. So this is going to be theta equal to 90 degrees, which means this now is going to be sigma x1 and this is going to be sigma y1. Okay, so let's jump back over to our plot and see what do our transformation equations say sigma x1 and sigma y1 are. So let me come in here again. I have theta equal to 90. Let's plot that. Come on down. Okay, here we are. This is our dashed line on the right hand side here. So sigma x1 is now equal to, again it's the blue line, is now equal to 0.25, and that makes sense to us because sigma x1 has taken the place of sigma y1. Okay, this is now pointing vertically upwards where sigma y1 used to be, and so it makes sense to us because we've rotated our set of axes. Because we've rotated our set of axes back over in the notepad now, it makes sense to us that the new value of this guy here must be whatever that guy was previously, okay? And so sure enough, sigma x1, when theta is equal to 90 degrees, so when theta is equal to 90 degrees, we get the value of sigma x1 is equal to whatever the value of sigma y1 was when theta was equal to 0 degrees. Okay, so all we're doing is, like I keep saying, the underlying state of stress isn't changing. It's just we're moving around the set of axes. And when we rotate our set of axes by 90 degrees, well then our sigma x1, or rather our x1 and our y1 axes, they just flip. And what was the y1 now becomes the x1, and what was the x1 becomes the y1, vice versa. Okay, so looking back over at our plot again, we can see that the green line, which is sigma y1, that is now equal to 1 Newton per millimeter squared. Okay, which is exactly what we'd expect, because sigma y1 is now aligned along what used to be the x1 axis. Okay, so all we've done is we've swapped values. The sigma y has become the sigma x, and the sigma x has become the sigma y. Okay, so there's no great mystery here, despite the fact that I might be making it sound more complicated than it actually is. There's no great mystery here. And then if we look at the shear, what have we got? Well, the shear is going to be, let me see, a minus 0.75. And again, that makes sense to us as well, because don't forget our set of axes has rotated as well. So let's just think about that in the notepad for a second. Now, remember, the state of stress hasn't changed. So the shear stress at theta equal to 90 degrees, it still goes in that direction, right? But now this is going to be, it's going to be on a positive face, right? That shear stress I've just drawn in red is on a positive face, but it's in the negative y1 direction, and that's what makes it a negative shear stress. And sure enough, when we go back and we look at our plot of our transformation equations, we see that at that point, when theta is equal to 90 degrees, the shear stress has become negative. So it all starts to link up, it all starts to tie together and make sense when we start plotting and visualizing these equations, and we combine them with what we know about our sign conventions, and we combine them with what we know about our transformation equations. Now, what is the other big headline here? What's the big takeaway message? I think the biggest one here is that the values of normal stress that we started out with, remember, sigma x equal to 1 Newton per millimeter squared, sigma y equal to 0.25. The headline here is that those are not the maximum values of normal stress that develop in that particular element, right? It turns out that if I was to take a cut through my structure that exposed an element that was orientated at, let me see, what is that, maybe 30 odd degrees, 33 degrees? If I was to take a cut at 33 degrees and consider the normal stress that develops on a plane orientated at 33 degrees, I'm just eyeballing it from the graph here, well then actually the normal stress on that plane is at nearly 1.5 newtons per millimeter squared. So it's nearly 50% greater, and therein lies one of the key motivations for what it is we've been doing here. The whole point of all of this derivation and, you know, getting these transformation equations is for us to be able to identify the fact that for the what we thought was our, you know, where we started, our original state of stress, sigma x, sigma y, and tau xy that we started off with, it turns out that those are not the largest magnitudes of stress. And that's a key result for us as engineers. We're going to want to be able to come along, and for a given state of stress in an element, we're going to want to be able to come along and identify, well, what is the absolute maximum value of the normal stress, and on what plane does it occur, at what orientation does it occur, and similarly, what are the maximum shear stresses and what are the planes they occur on. So that's the next evolution of our discussion here around is going to go down this is going to start looking at this. We're going to start thinking about, how do I identify what are the maximum normal stresses, what are the maximum shear stresses, and what are the orientations of the planes on which they occur. So we'll take a break here, come back in the next video and start thinking about that exact question, identifying maximum values of stress and on what planes they occur. Excellent. Okay, take a break and we'll pick it up in the next one.